Wunderbar. So we'll start off talking about metallic bonding. And metallic bonding, here we're talking about mostly those transition metals. So if you would be so kind as to get out a periodic table. You can all do this, you know, hyped up on sugar cookies at 2 in the morning after, you know, a binge of family time, I'm sure. There are those things right in the middle. And when we were drawing electron configurations for all the groups, we said main group is real easy. S, they end in S or they end in P, and they're all on the same main energy level. Fantastic. But there was something weird about that D block. Okay, so if we take as an example, let's take titanium. And titanium has how many electrons? It's got 22 electrons. And we said that with the D block, the valence electron concept is a little bit odd. So titanium is in group 4. And so titanium's electron configuration, if we wrote noble gas configuration, we would use argon. And then we would have 4s2. And then we hop back down to the 3d, remember? And we would have 3d2 if everything goes easily. Well, what happens in metals, in those transition metals, is these electrons become delocalized, and they kind of roam all over the place, like, you know, whee, I'm a D, no, I'm an S. It's this little bit of chaos that gets introduced. It's because there are lots of vacant orbitals in those D subshells. You know, you've got 3d2. That means of 10 D orbitals, only 2 of them have anything in them. So it happens a lot within the Ds. You also get some crossover with the S's because the 4s and 3d are pretty close. So what we end up with, it's typically referred to as a sea of electrons. It's like a giant swimming pool into which they all jump. And you get this sort of fuzzy cloud of free-moving electrons. They move pretty easily. Well, remember, you've got down in the center all these little positive nuclei. And those positive nuclei are tremendously attracted to all of those free-moving electrons. So rather than, you know, individual bonding happening between one positive point, one negative point, we get this sort of massive, what we'll call basically a massive sea of attraction. And so this positive nucleus is attracted to every electron out there, as is this one. What that means in practical terms is that you've got bonds of attraction, forces of attraction, running in every direction. Let me ask you this. If I take a nice piece of copper and I hit it with a hammer, will it shatter? No. Can I bend a nice piece of copper? Yeah, sure. Can I hit a piece of salt with a hammer? And will it shatter? Yeah, it'll shatter like glass. So in these metals, and this is metallic bonding, the phenomena we're describing here is metallic bonding. It's bonding in metals. What we see, so if we remember when we had our ionic compounds, which tend to be very brittle, when we hit this thing with a hammer, there's our metaphorical hammer, we shift all these layers. And once we shift them, now the bonds are not of attraction but of repulsion. And so this thing shatters. It goes flying off in different directions. Well, with our little metallic bonding, where we have all these little positive nuclei swimming in a sea of electrons, and that is the term that is most commonly used, just sea of electrons. These forces of attraction are running in all different directions. If we hit this thing with a hammer, are suddenly the forces not going to line up? No. They're not dependent on that very orderly system of attraction. So you can hit it with a hammer, you can bend it, you can pull it into a thin wire. Malleability, ductility. And those bonds of attraction are going to stay strong internally. So this thing is not going to just shatter apart. Now, because there are all these bonds of attraction running in multiple directions, when you have strong internal bonds, what does that mean about melting point? Tends to be high or tends to be low? Tends to be high. What do you know about metals and their melting point? If I give you a chunk of iron and a saucepan to stick on your stove, can you melt that for me? No. Metals tend to have very high melting points, and it's because of those internal forces of attraction. So that's one of the characteristics that we see in metals because of their metallic bonding. Okay, so we talked a little bit about this point, that they're malleable and ductile because of those forces of attraction that are running in every single direction. But let's talk about this phenomena. You all know that metals are good conductors. You've known that since you were probably in 5th or 6th grade. We talk about it a lot. Well, metals are good conductors of heat and electricity. And you also know that if I have a piece of metal pipe and I'm heating up one end of it and I ask you to grab it, you're not going to. Because your real world experience tells you if one end of that metal pipe is in a fire, then I should not grab the other end. You also know that if you see a chunk of metal wire that's stuck in an electrical socket, you shouldn't grab the other end. I had a student once who didn't know that, but that's a different story. They're good conductors. Why are they such good conductors? Here's what I want you to imagine. Imagine a garden hose. Actually, better yet, I would like... Oh, I never pick on that end of the room, do I? Okay. Sarah, Katie, Ryan, Alex, Jeremiah, and Hannah. I would like you all to stand up, and we'll close the green cabinet, and I'll have you stand. So we'll reiterate that since you can't see, for those who are absent, you can't see in the recording here, you can't see what we did in class. But if we have a garden hose that's full of water drops, which are really our little electrons, and we add an electron to that hose, it's going to boot one electron out the other end. And that's exactly what happens with a piece of wire when you conduct electricity through a piece of wire or a flat piece of metal or anything else. Metals are very easy to electrify. They're easy to pass current through because of this. And it's the same, they conduct heat well because heat is really just atomic motion. Heat is how fast your atoms are moving. So because parts of their atoms are very free to move, their electrons are very free to move, they can transfer that kinetic energy very easily. So again, the properties of the substance all come down to forces of attraction and repulsion at the atomic level, which I find amazing. That like how stuff behaves in the real world, things that I can touch and handle and bend and whatever, it's governed by the forces between their atoms. I find that astonishing. So that's metallic bonding. Okay, so this is where we start to get into the stuff that will carry you into the molecular geometry lab. We said in metals, the arrangement of the individual atoms determines their characteristics. In ionic compounds, the fact that these ions are all packed together and there's heavy-duty attraction between the cations and anions, that determines their characteristics. Well, in molecular geometry, things that are held together covalently, the same is true. So the shape of the molecules can actually determine how the substance behaves, and we can figure out the shape of the model. And this is where we come down to testing and model making. Did any of you, when you were in biology, see the movie Photo 51, The Secret of Rosalind Franklin? Okay. Rosalind Franklin was a researcher. She did crystal X-ray I always screw it up. Anyway, she took X-rays of DNA molecules. X-ray crystal diffraction, that's it. And from sort of the shadows that the atoms cast, she was able to make really good guesses about the structure of the DNA molecule. Prior to having the ability to do that kind of work, it was all guessing. There was no actual knowledge about the shape of individual molecules prior to probably the 1930s or 40s. Well, actually, I guess Rosman was doing her work in the 40s and 50s, late 40s, early 50s. So anyway, prior to that point, there wasn't a whole lot of information about how molecules were shaped. It was guesswork. Today, with any kind of molecule, it's a combination of things. Now, these days we have amazing computer technology that allows us to figure out molecular geometries really fast. But it's also understanding how things behave, how the forces of attraction and repulsion work, and making guesses about it. And then you confirm those guesses with, either nuclear magnetic resonance imaging, which is basically shaking up the molecule until you see what's in it, or taking X-rays of it. What we're going to do is some model making. So how atoms are arranged in a molecule is as determinate of the characteristic of a substance as the ionic or metallic bonds. I think this is the slide we just talked about. I double clicked it, didn't I? Yeah, whoops. Okay, so this is where we get to Vesper theory, and I realize I spelled it wrong in this week's learning goal. But the first learning goal for this week is that you're going to be able to use this Vesper theory to predict the shape of a molecule. And this is really the whole game. Vesper stands for valence shell electron pair repulsion. And it's based on the very simple thing that you know. Positive repels positive. Positive attracts negative. That's it. I mean, you've known that for a very long time. And so when you have something, let's say, like oxygen, and remember that oxygen has two unshared pairs. Let me change that and use that for my dots. Oxygen has two unshared pairs. It's also got two other sites where it can bond, and it bonds to hydrogen. Well, those unshared pairs want to be as far apart from one another as possible, because those unshared pairs are two electrons. If you're a room, a balloon, a chunk of cotton candy with two negative charges in it, you want to get as far away from the other balloon with two negative charges in it as you can. Well, these little hydrogens are what? Basically two protons. Those want to get as far apart from one another as possible. Okay? So, like charges always want to push as far apart from one another as possible. How far apart can you get from something else when you're attached in the middle? Let's explore that. We end up with this weird geometry because the unshared pairs and all the things that are attached to it all want to get as far apart as they can. I want everybody to make sure they get to see that. So that's Vesper theory. Let's explore that in its, well, let's draw water. So we've got our central oxygen, we have two unshared pairs, and we have our hydrogen. Now, we can't really draw that four-dimensionally or three-dimensionally on a piece of paper. So what we show is that this thing is bent. That's where we get the Mickey Mouse that we usually draw. Because this thing is bent. And of course it's got these unshared pairs that we show down on the chin. So Mickey has a very negative chin. What we're predicting here is the shape of the molecule. Vesper theory gives us some distinct implications. Vesper theory says if you have two things that are bonded to nothing but themselves, and let's see, well, nitrogen. So nitrogen triple bonds to another nitrogen. They each have an unshared pair there. What is the furthest away that those unshared pairs can get from one another? Well, to be on the outsides. What is the furthest away those nitrogens can get from one another? To be in a straight line. So, in something that is just two atoms, it's always going to be a linear arrangement. It will be a linear arrangement because that is as far apart as they can get. We'll move this up there. When you're done, you can just set it. Oh, nobody over here got to see it, so I'll start it off with Emma. Okay, if we have three things that are bonded together. Oh, you saw it? Okay, did you guys? Okay, wunderbar. Thanks. So CO2 is a good example. So if you remember, we had double bonds. Looks like, whoops, looks something like that. Okay, that's also going to be linear. Now, there are unshared pairs here, but they are not on the central atom. If they're not on the central atom, they're not going to influence the geometry. So these guys do not change badly spelled, badly written. The only place we're looking for unshared pairs to change geometry is on the central atom. But if we've got three things hooked together, that's going to be a linear molecule. Do that. Now, if we've got something that has four atoms on it, the farthest apart that four atoms can get is what's called trigonal planar. So trigonal makes you think what? Triangle. Sure enough. Planar, this is a tougher one. What it means is all in the same plane. So I've got this little beauty here. I'm trying to think of something that meets this. Do beryllium. Yeah, beryllium trifluoride. Boron trifluoride. Okay, so we get a central atom with three things attached. If you look at this thing flat on, they're on the same plane. If you look at this on the edge, there's no deviation from the flat. This is essentially two-dimensional. Do we want to pass that around? And that's what's called trigonal planar. It's a triangle, but it's all on the same plane. Now, if we have 5 atoms, it gets a little bit more complicated. Whoops. We'll move that up to the trigonal planar, roughly. If we have 5 atoms, that's when they tend to push out of the flat plane. And they end up in what's called a tetrahedral arrangement. And it's a tetrahedron, meaning it's got 4 points. So it ends up looking like this. You'll notice I cheated on something. You'll learn what later. But it's like a jack. If you've ever played jacks, this is a lot like a jack. It's always going to land with 1 point up. So, let's see. Well, we'll do methane as tetrahedral. And tetrahedrals are really tough to draw in 2 dimensions. So we typically draw them like that. If you go on to take organic chemistry, what you start to do to draw tetrahedral molecules is you draw, let's see if I can remember this. A solid triangle means it's pointing out towards you, and a dashed triangle like that means it's traveling away from you. So you would draw it something like that. And that's supposed to show dimensionality. It doesn't do a great job, but that's a tetrahedral arrangement. 5 molecules, tetrahedral. So you're now at a point where you can predict, based on how many things are attached, what shape it's going to take. Does your Lewis structure, I mean, right there's a Lewis structure for methane. Does it show that it's tetrahedral? No, again, because we're working in 2 dimensions, and this is a 4-dimensional object. That's why in your lab, you're going to both draw it and build it. Maybe I should have you take a picture of your structure next to your Lewis structure next to your model. That might not be a bad idea. So you get the comparison. Okay, now, sometimes we have both atoms and unshared electrons attached to the central. Water is a case in point. So water has 2 hydrogens attached. The hydrogens want to be far from one another. But it also has those 2 unshared pairs on the central atom. And again, unshared pairs only affect geometry if they are on the which atom? Central. I'm going to need that methane back, ma'am. This was my cheat. So water, thank you, ma'am. Water is a bent molecule. It's a bent molecule. Those hydrogens are bent down and away from the oxygen because those unshared pairs push them down outside the plane. It's not linear, even though there are 2 things attached. There are 2 things attached, but there are also 2 unshared pairs that we have to account for. What if we have, let's get some of those other models. What would happen if we added an unshared pair here? Would it just sort of hang out on top? Would it change the way these are structured? Yeah. And what that ends up looking like, well, I guess I didn't need to do that. That was silly. Is this. So these hydrogens, in this case, all get pushed down by this unshared pair. So this went from being, 3 atoms attached, trigonal planar. If there's an unshared pair on the central atom, they're all going to get pushed down. And this is called pyramidal, because if you were to fill in walls on this thing, in essence, what you have is a little pyramid. These things are no longer in a plane with the atom. It's going to make more sense, I think, as you go and as you start building these things, which is why we're going to spend 3 class periods building models. So let's talk a little bit. And this is all, here's the weird part. When you look at a traditional model, you can't see the unshared pairs. That's why I like these model kits, because they have the little unshared pairs. So there are 3 things attached. How do you know it's not like this? There's some invisible force that's deforming this whole thing. Yeah, it's the unshared pairs. And so having a model kit with unshared pairs makes that really obvious and really visible. Okay, hybridization is the next thing we're going to talk about. This will be handled in more depth if you were going on to a college chem class. I just talked to a student who came back who said, yeah, my first year of chem was pretty easy, but we talked about hybridization a lot more than we did here. Yeah, we'll touch on it, we'll skim it, and if you go on to take a chemistry course at the college level, you'll go into a lot more depth. We will mostly talk about this after we do the lab. So there is one column on your lab that you're going to leave blank because it's going to be talking about the hybridization. And I want you to have the physical experience of seeing the models and having pictures of them before we discuss this, because I think it makes more sense that way. So with that, let's talk a little bit about the lab. So looking at this side, which is the sort of data table, for each compound that is listed, you're going to look at the number of lone pairs on the central atom. That could be 0, 1, 2, it depends. We're only interested in lone pairs on the central atom. How do you figure out what's central? Carbon if it's there, or if there's only one of it, yeah, if it's a singleton, NH4, you can bet nitrogen will be in the middle. The other possibility for the central is the least electronegative. So least electronegative is typically going to be in the center. You're only concerned with the number of lone pairs on the central. In the second column, and we'll walk through this together again tomorrow, the total number of effective pairs around the central atom, you can make a note to yourself that that just means number of things attached. So if it's got two things that are each attached with double bonds, there are still two effective pairs. So that total number of effective pairs really just means number of things that are hanging off that central atom. And then we'll talk more about the third column tomorrow when we start. The angle between the bonds around the central atom, you are actually going to measure those with protractors on these models. So you're going to actually get out the protractors and physically measure those. Then you will go to a chart in your book and you'll look up what the angle would be predicted to be. We'll see how, you typically, with these kits, if you're doing a good job measuring, you get within about a degree. So it's pretty good. Okay? I'll give you the rest of the time to do a quick summary of the procedure. You can do bullet notes. It's 4 items, and we will start this when you walk in tomorrow. This is a nice lab in that you can wear open-toed shoes. So if anyone's planning on flip-flops tomorrow, you don't have to change your plans. And you don't have to put your hair back because we're not lighting anything on fire and we're not using any chemicals. You will sit at the lab tables and just work on this for the period tomorrow and then 2 periods the following day. Yes, sir? No, you do not have to wear goggles. No goggles, no worries about dropping acid on your toes, and no hair back. That's it.